Alright, so, everybody awake? Everybody got a calculator? You need a calculator for this. Okay, you should find 4.3 in your textbook. It's page 327, so this is 4.3. Find that. You need a calculator. We're going to do a couple things first. Y'all listening? Alright, number one. We need to know a couple of these terms over here. Before we talk about those terms, though, I want to make sure you know some things that you should already know. So that is number one. We should know about a quadratic function. What's a quadratic function equation? General parent equation. Y equals? Oh, y'all better know it better than that. X squared. Don't overthink it. All right. Parent equation for a quadratic is y equals x squared. Quadratic. Okay. You should also hopefully know the cubic equation function, which is y equals x cubed. All right. So we've got two different parent equations. They look very differently. The quadratic equation is a parabola. What's the most important point? The vertex. Okay, this one has a vertex. What happens in a parabola in terms of symmetry? Okay, this has what type of symmetry? Line symmetry. That's the algebra term. What's the, just so you can connect learning, what is the geometry term for the symmetry? Somebody said it. Okay, if you rotate it, it has to twist or turn. It's not going to rotate. It's reflectional, meaning it's like a mirror. This is also called reflectional or reflectional symmetry, which means, and these talk about the type of function it is. This is an even function. Did we talk about that before? Okay, even function. Now, an even function means, there's a C in there. An even function means it has symmetry through a specific line. What line? It's always going to go through the vertex. It's always going to have an axis symmetry. What specific line? Anybody know? Well, the origin's a point. It's not a line. The y-axis, x equals 0. Okay? If you have a parabola that goes right through, the vertex is on the y-axis, then you can fold it through the y-axis and then it creates an even function. So this is when you have line symmetry through x equals 0 or the y-axis. Okay, you also have an even degree. This is different. And what does an even degree refer to? Let's say something has an even degree. Go ahead, Lily.
So, degree is the largest exponent there is in the equation. So
alright. This is the power or the exponent of the equation. Okay? Could you have an even degreed function that is not even symmetry? Yeah. What could you do to this equation right here, this graph, this equation, to make it not be an even function, even though it's still an even degree? What could you do to it? Okay, so what could I do with this graph, in other words? The words. Move it left or right. Does that make sense? If I took this graph and just moved it over to the side here, so it was like over here, it would no longer be, by definition, an even function, because function refers to the graph. Is that okay? Alright, you need to know cubic then. Oh, by the way, what's the parent equation? Sorry, not the parent equation, the parent table. You should know this by now. This is quadratic. -2, -1, 0, 1, 2, and then what's the y values? 4, 1, 0, 1, 4. And from that we can translate anything without a graphing calculator. Okay? Cubic equations you need to know. Have we graphed a cubic equation yet?
Yeah.
Yeah? Okay, so the most important point again is 0, 0. It's no longer called a vertex. This is now called an inflection point. It acts like a vertex. Alright, but it's an inflection point. It goes up to the right, down to the left. We've talked about that already, correct? Okay. This does not have line symmetry. This has... Okay, point is the algebra. And I also heard people say the geometry, which is rotational symmetry. And this makes what's called an odd function. An odd function if and only if the point is what specific point? The origin or 0, 0. Okay, what's going on? And we then have what's called an odd degree. That just means the power, or the exponent. So again, we could have an odd degree, but not an odd function when you graph it. Okay? Make sense what's going on? If I move this right or left, or even up or down, it might change that. Hey, how's it going? Are we okay with that? And then last is our generic parent table, same x values. Tyler, what does our y values become?
So the first is 8.
Careful.
Oh,
Negative 8. Okay, negative 8. Keep going.
Negative 1.
Negative 1. 0. 1. And 8. Alright, so you can, are we okay with all this? Quick review? We need to know those things. Alright, here's what we're going to do. Today on 4.3, you guys have your things here. Biggest thing we're going to do today is to remember how to dilate, reflect, and translate. Okay, what's a dilation? Rohit, what's a dilation? Okay, so going in our transformation rules, y equals a, b, x minus c plus d. Put a little f there. Which letter is going to dilate? Or letters? A or B could dilate. Stretch, compress is a dilation. Is that okay? How do you reflect? Negative, right? Negative A or a negative B. And translate refers to what? C and D, meaning what? Moving, right? Right, left, up, down? Is okay what's going on? Okay. Let's see. We're going to talk about even and odd, which we kind of just referenced. That's kind of a review a little bit for us. Right? And then we're going to explore different types of graphs, which we're really going to get into next class period. What's today? Wednesday? Yeah. So Friday we'll really get into that a little bit more often. Okay. Quartic, we're not going to do a whole lot with these, but just know the names. Okay. A quartic function is x to the 4th power. What's its degree? 4. And a quintic, I'll let you guess. Not guess, but use your synthesis. X to the 5th power, which means it's a degree of 5. Which one's the odd which one's the odd function? X to the 5th, right? Pretty easy. Odd numbers are odd functions. Are we okay? What's going on? Alright, it's a big overview of what we're doing today. Are we ready? Alright, flip over. You can use your calculator, I don't care. I want you to read through problem number 1. This is talking about this parent function, which we've already talked about. You may not need your calculator because you probably know this already. We've talked about it a couple times in class, but feel free to use that. This table that they give us, it's not a bad table. They want you to use your knowledge of reflections or point symmetry or line symmetry based off of the parent equation. I tend to use the 5 points that we know for our parent equation that we just talked about. I like to use all 5 points. The book just uses these 3, and then it tells you to reflect or rotate based off of the power. Both of them are correct. Whatever you would like to use is perfectly fine with me. I tend to use 5 so I can see the movements happening. But I want you to go through that with your table. Do number 1. Talk about number 2 with symmetry. We've talked about that. And then I want you to read problem number 2, specifically all these things, and see if you can find some similarities or if you understand what this is talking about. All right, I'll give you about 5 minutes to do that with your table and we'll come back. Go. All right, let's see. Arjun, did you guys look at this problem number 2? Can you kind of summarize what this table is telling us right here, this big symmetry here? Okay, listen, Arjun, real quick. Make sure you're all getting the same answers. Go ahead.
So basically, it's like a quadratic function. So
Okay.
if the a is greater than 1, then it's a vertical stretch. If it's a negative, then it's a reflection.
Okay. So all of these are the A movements. We got all the A movements, and these are the transformation rules, right? Okay. So A will either vertically stretch, vertically compress, or reflect if it's negative. That just basically means it's negative. And then these are all the B rules. This all looks familiar, correct? Yeah. We've done this like since the 2nd week of school. All right, the B movements, the C movements, and the D movements. Are we okay with all those things? We haven't really done anything. It's just a reminder that even though we have a new parent function, the rules are the same. So basically, the nice thing is you just got to know a new table, you got a new shape, but you're not doing anything new outside of that. Are we okay with that? All right, on the back side, we want to create, I don't know if you've looked at this yet, we want to create this is called coordinate notation next. Okay, coordinate notation says you take a random xy from the parent, and then you're going to move it. It's kind of like the heading of your table. All right? So what happens if we have a vertical dilation? Does that affect x or y? Y. And if you're not sure, vertical right there tells you. right? So that means a generic xy, since the x doesn't move, we're going to call that x because it stays the same. But y moves. How does y move? Well, there's not a 4 there.
Oh, by A, sorry.
By a. What do you do with a? Do you add it? Do you subtract it? Do you divide it? Do you multiply it? What are you going to do with it? Multiply it. So this table would be a times y. Does that make sense what's going on? So for example, if you had an equation y equals 3x cubed, right? That means all the xy's in your parent table would turn into x comma what? 3y. They would get 3 times bigger. The y's, only the y's, not the x's. Can y'all see this okay? All right, so what I want you to do is fit that table right there in coordinate notation, and we'll talk about it in a second. Go. Going through our table here. Let's see, if you factor by horizontal dilation by a factor of b, this is the one that most people miss, and they forget something important. What do you always have to do for the x values? You always have to solve backwards for the x values, right? So if you have a factor of b, for example, here's my example right here. If you had an equation y equals, all I'm going to do is put parentheses, 3x cubed. All of a sudden this becomes the b value. Why? It's inside the parentheses. Now the graph looks the same. This graph is going to look the same as that graph ultimately, right? Kind of the same. But it's reference. A difference. This is moving x values, whereas this one moves y values. Ultimately they tend to end up looking the same pretty much. But in my coordinate notation, my x values are actually going to be a third as big. This is a horizontal compression. When you stretch vertically, what are you doing widthwise? You're getting skinnier. Does that make sense? That's why these two graphs look the same, but this is telling us the y's get taller, while this one's telling us the x's get narrower. That should make sense, right? Because if you take something and it's not expanding and you just stretch it this way, then it's going to thin out. Does that make sense? So what is the correct way we would write this? I would write it as 1 over b times x comma y. So make sure you understand it's always the reciprocal for the b value. Okay? These ones everybody did fine. This was x plus c comma y. Garrett, what's this one? X comma? Well, there's a y in it. What are you doing to y? Plus or minus. The I just put plus because if you add a negative, it's automatically minus. Does that make sense? And then we'll put all these together. Kelly, I'll answer your question in a second. We're going to put all these together down on here. Alan, what'd you get on this last one? 1 over b times x, okay? Plus c, comma? ay plus d. Everybody okay with those? All right, Kelly, what's your question?
I was wondering why b plus c instead of minus c.
Because the equation will say minus c, but you always do the opposite action to solve for x.
Right. So I was just wondering why.
Yeah, so it's just so if your equation said as an example y equaled x minus 2 cubed, that means your x comma y ordered pair will shift to x plus 2 comma y. So you're just going to do the opposite. Does that make sense?
Yeah.
And if you add a negative, then it's still minus. So you can get away by kind of cheating the system. It works both ways. Okay, make sense? All right, what I want you to do with your table then, if you flip over to the next page, I want you to try number 2. A, B, C, D, flip over, 3, A, B, C, D, and then 4, A, B, C, D. They're all very similar. Okay, now what I'm going to tell you is you can do the books method, but if you do the books method, they're only giving you half of the table points. Okay? I'm not saying the book's wrong. The book is actually right. They're trying to stretch your mind a little bit to understand symmetry, but if you only graph these, you're not going to graph the whole function. Does that make sense? So I tend to like using my parent table for a cubic equation and then translate that according to our rules. I like to use that instead of 3 points. I like to use all 5. I'll let you do whatever you'd like, but I'm going to give you a couple minutes here. We'll talk about it when you're done. Go. All right, let's go ahead and talk about just number 2 here real quick. I want to make sure you guys are doing the right thing, and the other one should hopefully Match. Okay, first off, they're telling us C of x is the parent cubic equation, which I know that everybody saw that, which means this is our C of x parent table. They're picking these random points, which are really just these 3 points. As I said earlier, it's incomplete because you didn't get the negatives, but you can understand symmetry, it rotates, so the x values are opposite and the y values are opposite. Okay? As long as it goes through the origin, that's always the case. I don't like to do this if it's a horizontal, right or left, up, down, because then it doesn't always work the same way. But they're telling us that g of x is 2 times c of x. All right, Satvika, what does that mean?
Okay, so that means your c is being removed.
Okay, so is this number 2 an A, B, C, or D?
The 2?
Yeah.
That's a.
This is an A number, right? This is an A equals 2, so it affects x or y? Y. How does it affect it? Add, subtract, multiply, divide? Multiply. So basically my table turns from x comma y to x comma 2y. You guys got that, right? So then I would graph these points. Let's see. X never never changes. Y is going to double. So negative 16, negative 2, 0, 2, and 16. And I would then graph these points. And if you did the book's work, it's 0, 0, 1, 2, and 2, 16. Notice here 0, 0, 1, 2, and 2, 16. Does that make sense what's going on? Okay. How is that different on B's equation down here? Avi, what does this happen on B? What's happening? Okay, so the y values are taking half, right? So this is x comma half of y, dividing the y values by 2. All right, so my ordered pairs are 0 comma 0, 1 comma what? 1/2, and 2 comma 4. And you would graph those points as well and see the different movements. The big thing is, let's talk about symmetry. Do these symmetries here, do these things change the symmetry of the two equations? Does the symmetry change? You should say no. Why no? It's still point symmetry. Or sometimes we call point symmetry what? In the geometry terms? Rotational. Because the origin is preserved. So the graph upside down is still the exact same because it still goes through 0, 0. We didn't move it up, down, left, right. Okay? Which means we still have an odd function because, like we just said, it still has an, what do you call that? An inflection point through 0, 0. So regardless of how wide or how narrow, right, or even wider, regardless of how that is, if I turn my graph over through that point, my graph is still the exact same. Does that make sense? That's an odd symmetry. As point symmetry or rotational symmetry. I hold that point still the exact same graph, top and bottom. Does that idea make sense? All right, so what I want to do is you should hopefully have a chance to finish 3 and 4. I'm not going to go over those just yet. We'll talk about them a little bit later. Also 5 and 6, we'll talk about those. I want to then go to something different that we will need, and we'll come back. And that is, let's start writing equations. So I'm looking at problem number 3. Everybody find problem number 3. Okay, here we are, problem number 3, page 338 right here, 338. I'll have all of these answers. Your task is to finish those other ones and then check them before you can move on to the next part. Okay? What we're going to do now is we're going to write the equations. We are going to write the new transformed equation. Okay? They are going to give us an equation, f of x here. Right? This f of x graph is what parent equation? What's this equation going to be? This is y equals, or f of x equals, x to the third power. This is x cubed. You should know that shape by now. It goes through 0, 0, 1, 1, 2, 8. And it's the little, what do you call it? Odd symmetry. So it's an odd function. We okay with that? All right, what we're going to do is we're going to transform from this graph to this graph. I'm going to do the first one with you. Now, we are going to write this in function notation. What does that mean? Okay, so if it's function notation, we want to have that little f in there. What do we not need? We don't need x cubed. So it's going to be like an a times f bx minus c, if necessary, plus d. We're not going to put a power there. Make sense what's going on? So we're not going to worry about knowing that it's the cube power in our equation. We know it's the cube because we're moving this cubed graph. Is that all right what's going on? All right, so most important point is the inflection point. Find the inflection point on the other graph. Put a little dot there and make reference of how it moved. So how did this point move? Down 4. I like to sometimes write myself some notes. It went down 4. That tells me which one of my letters. A, B, C, or D. So it tells me my D number is, if it's down 4, it's got to be negative 4. That's my D number. I know that now. Okay. Did it move right or left? No. If you're not sure, 0 stayed 0. Make sense? But the other 0, the Y, went down 4. Is that okay? So we've got the D number, check. We knew that there was no C, check. Now you're writing your own equation. Remind yourself, A and B are the exact same, except A moves the Y values and B moves the X values. So if you were going to pick your own equation to write, which one would you prefer to write in, an A number or a B number? Always A, because then you don't have to worry about flipping it, right? So we typically don't do B unless they force us to do B. So we just need to know the A number. Well, A refers to a stretch. Make sense? So what we're going to have to do is we're going to start writing our equation. Our equation is going to start Y equals A X didn't move right or left. Q, this is F of X cubed, and then minus 4. Okay, what's going on? We got to figure out the A. All right, in a graphical sense, the A value is always the next X, and then the A value is how far up or down does your Y value stretch. So if you had your parent table, 0, 0 is your inflection point. The next X, according to the parent, has a stretch of 1. That's an A value equaling 1. Does that make sense? It's kind of like slope, almost. It's not really slope. What is this stretch over here? If I go to the next X, that distance right there is my A number. Let me know what that is. What is it? 3. How'd you know it's 3? Goes from a negative 4 to a negative 1, and it's up. Negative 4, negative 2, negative 3, negative 2, negative 1. It's going in a positive direction. So that tells me my A number right here is 3. It's a stretch of 3. That only works on a graph if your X value is the next X, and then you go find Y. If they did not give us this point, and we only knew this point, we'd have to plug into the equation and solve for A using this X comma Y ordered pair. We've done that before. Remember how to do that? You plug in 20 equals A times 2, and you'd have to use cubed then. You can't use the F function. Minus 4, you would still get the same A value. Okay, so we're going to write this equation. This equation is G of X equals the A number, 3, times F's function, because we're going to use function notation. X, we didn't move it horizontally. We don't need a cube because we're calling up the function by F, and then we're going to minus 4. There's our equation. Make sense? All right, I'll pause this video. You guys need to do the next two, which is this G of X equation and this other G of X, B and C. Go.
All right, let's go ahead and come back together. You need to check these before you move on. These we're just going to write the new equation. Listen up real quick. Number 2 down here, we're going to write the new equation based off of how they have written it. Again, this is kind of a review. Our P of X equation is X to what power? 5. Is that an even or an odd? Odd, all right. So that tells me it's going to probably, by the way, all the odd functions end up looking about the same generically, and all the even functions look about the same generically. We're going to learn that in just a second. But we are going to write this equation for, is that T of X? T of X in terms of X. All right, so we're going to put it from function notation into how you would graph it on a graphing calculator, like Y equals on a graphing calculator. The calculator doesn't understand P of X. It understands X cubed or X squared or X to the 5th in this case, right? So this equation would turn, oops, it's a T, T of X, 0.5 is A, B, C, or D? A. So it's going to be 1/2. I don't care if you do a decimal or a fraction. And then we're basically going to cancel out the P value, because that's just referencing this equation. And we're going to, at the end of the parentheses, put what the power is. That's all you got to do, is work it backwards. Make sense? So our equation no longer has that p of x. It has a parentheses, negative, whatever's in the parentheses to that power. And this now we can actually graph on a graphing calculator. The calculator understands what function we're doing. Whereas before we were writing function notation. This is function notation. Now we're going back and we're writing it in, like, what would you call it? Just an y equals, or an equation that you can graph. You can't really graph this. You have to know what p of x is. Now I don't need to know what p of x is. I can graph it. Okay? So you're going to do the same thing on the next ones. Let's see. On B, we'll do that one real quick together. This one would be t of x. All we do is take out this little p and plug in what its power is at the end of the parentheses. So what would this equation turn into? Henry, can you write this equation for B for me? This one right here. B on page 340. You're going from function notation to graph notation. I don't know what the right term is for that. You're not sure? All right, who can help Henry out? Can we get some help? Go ahead. So 2 is an A number, Henry, so we're going to put 2 first, because A goes first, right? There you go, x plus 3. To what power, though? 4th power. Okay, so you drop the function notation, you insert the exponent, so the graph now knows it's an even function, and the graphing calculator, if you were to go to this, y equals, you could now type this equation that I have right here in, and it will understand how to graph it. Does that make sense? Are you okay with that? All right, you make sure you can write the equation for C, and we'll check it here in just a minute. All right? Okay, last thing I want to do with you is to talk about some symmetry. Everybody find the last page, 347 right here. It looks like this. This is the last thing we're going to do together. All right, we're going to do a lot of stuff here, so pay attention. We're going to write all over this page. This is going to lead us into not only understanding what we're doing now, but also next class period is going to make it a lot easier. Okay? All right, first off, linear equations. What type of a linear equation is this one? Positive. What type is this one? Negative. So everything's going to be a parent equation. So what I'm going to do is I'm going to write the equation over here. Y equals x. And over here I'm going to write y equals negative x. Okay? And eventually we're going to have to be able to graph random polynomial equations based off their factors, and to do without a calculator. And to do that, we need to know what a factor is. All right, factors. What are the other names for factors? Roots, solutions, x-intercepts, etc. Okay, and we're going to have to be able to do all those things. Okay, so the first thing we need to know is obviously where it touches the x or y axis, but then we also need to know something very important. I'm going to draw like a little coordinate grid here. And we need to know what's called end behavior. This is new. Has anybody ever heard of end behavior? Okay, that's why we're going to talk about it. End behavior means what's happening on the ends of the graph. In other words, these arrows. Does that make sense what's going on? Because if I told you to graph an equation, you might be able to put the dots where the graph crosses the x-axis. You might even be able to put the dots where the graph crosses the y-axis. Right? But you might not know what's going to happen after it crosses through those things. Making sense? Which way does the graph ultimately point? Is it pointing up? Is it pointing down? Is it pointing both up and down? Where is it pointing up and down? So end behavior tells us what happens on the ends of the graph. Okay? And you write this a little bit funny. I'm going to show you how to write it, but it's a really simple process. All right? You always write the end behavior in terms, you start with x's because x's generates y's. Right? Inputs versus outputs. All right? So you're going to say as x, and then you're going to put an arrow, and you're going to say infinity. And you read this, you say, as x approaches infinity. You're going to put a comma. You're going to say f of x. What's that mean? Y. Y is going to do something. So when x's approach infinity, y is going to approach something. And we're going to look at our graph. So where is x approaching infinity? How do you graph an x? An x number can only graph on the x-axis. Which way is that is my question. Left and right. So x's can go left or right. If an x is going to infinity, which way is it going? To the right. We got that? So as my graph goes this direction, what is the y values doing? going up to infinity. Does that make sense? So what I'm going to do is I'm going to say as x goes to the right, this is how I would write it mathematically, y goes up, and y's ups are also infinity. And now I understand on the right side my graph has an arrow pointing up. Well, here's the right side and it points up. Does that make sense? I would also then have to say as x approaches what now? Negative infinity, because I know this end side, I need to know what this end is doing. So as x approaches negative infinity, the x's approach negative infinity also. So this means as x's go left, y's go down. Does that make sense? Now, end behavior tells me nothing about the middle of the graph, but it does tell me what's happening on left side, right side. Is that okay? Now, if you have this equation, y equals negative x, our end behavior, EB, end behavior, is going to say as x approaches infinity, f of x approaches what? As x goes to the right, where's the y's going now? Down. I'll write negative infinity. Make sense? And then as x approaches negative infinity, f of x approaches positive infinity. So on the left side, the graph is up. On the right side, the graph is down. And you'll hear me say things. I don't like to write all that out if I'm talking. If I'm writing it on a test, or I have to, because that's the mathematical way you write it. But if we're looking at a graph, I would say the end behavior is down, up. Over here, I would say the end behavior is up, down. And the reason I would say that is because how do you read a graph? Left side to right side like a book. And if I say the graph is down, up, in your mind you should think, okay, I'm down on the left side and I'm up on the right side. Right? So it tells me pointing down here and pointing up here. Or if I said up, down, it would be up here and down there. Is that making sense what's going on? Okay, so this is a power. What degree are linear functions? This is degree 1. Because it's x to the first power. Okay? These are quadratic equations. What degree are those? 2. All right, I'm going to skip cubic for a second. These are called quartic equations. What degree are those? 4. If you notice, quadratics, degree 2, look the same as quartics, generically. The difference is the number of zeros that it could have. And a quadratic can only have up to 2 zeros, whereas a quartic could have up to 4 zeros. But ultimately, it's the end behavior that I care about. A quadratic function will have end behavior of up, up, or down, down. Making sense what I'm saying? Both sides will point up if it's positive. Both sides will point down if it's negative. So even functions have the same end behavior. Even functions are always the same end behavior. You okay with that? Cubic functions, x cubed or negative x cubed. Quintic functions, x5 or negative x5. They ultimately look the same. Any odd function will look the same, ultimately. The difference is how many zeros. Cubic functions could have 3 zeros, right? Like if this is the x-axis right here and this is the y-axis, 1 0, 2 zeros, 3 zeros. Or it could be all 3 at the same spot, which is the parent equation. Okay? Quintics could have 5 zeros, so it could be like 1, 2, 3, 4, 5. That's 5 zeros. But ultimately, the end behavior is what we care about. Down on the left, up on the right. This tends to look the exact same as a line for as far as end behavior goes, because a line does what? Down to up. Okay, so the ends are the same. All odds are opposite end behavior. It's either down, up, or up, down if you flip it. Does that idea make sense? If you took this graph and flipped it upside down like a negative A, now it's up, down end behavior. Is that okay with end behavior? So this is going to help us next class when we start graphing these crazy functions, because you're going to need to know the end behavior. You're going to know how many roots it has based off factored form. And then the last thing is what happens at each root. And we'll talk about that next class as well. Okay, so here's your task. Are you listening? I want you to go back through. I didn't give you enough time for all of these. I want you to go back through our problems here, and I need you to show me with your table, when you come back to your stuff here, you need to be able to show and check off, and I'll let you check off with my book. You need to show that you have completed this problem number 3 with the graphs, the table, and the answers. And then problem number 4, the graphs, the tables, the answers with the A's and the B values, okay? Then number 5, same thing. Then number 6, same thing. Then you can skip everything and then go to problem number C here. I've got them all worked out on page 340, writing that equation. And then, oh, you also have to be able to do these two equations on page 339, the page before. Make sense what you're doing? So you're just finishing what we haven't done. If you've got it, then you can come show it to me and I will give you the next page. You have 2 pages for assignments. Go. Okay, once again, when you have finished all of those, you need to check it with me, and then I will give you this next page. This is in class. There are 4 problems that you still have to work on in class. You're not done, okay? You're going to write or graph 2 equations without a calculator. You may use your calculator to check, but I want to see your headings and I want to see the correct tables based off your parent table. I would do all 5 points if it was me instead of just 3, but you can do all 3 and then know the reflection. I don't care. Then you're going to write the equation based off a graph, like you've done. Then you're going to write the equation based off of words. You're going to check that. I have the answer sitting at my desk. If you are comfortable with it, there is a yellow page for homework. That's what you'll end up leaving class with. But you need to check your bookwork and you need to check this page. You got plenty of time. You just got to get busy. Go.